Bismillahirrahmanirrahim. Dear students, today we are going to discuss about Hoffmann Loffler Freytag HLF reaction. This reaction is basically about the carbon nitrogen bond formation, and also this bond is in the cyclic form. That is, this new carbon nitrogen bond is formed in a cyclic manner. You can say this 5-membered in the form of a 5-membered cyclic ring, which is also known as pyrrolidine. So Hoffmann Loffler Freytag reaction is basically about the synthesis of pyrrolidines or the derivatives of pyrrolidines. The key concepts of today's lecture include the introduction to HLF, Hoffmann Loffler Freytag HLF reaction, some general features of this reaction, the mechanistic studies given by the Wazonek and Thilan about the mechanism of this reaction is discussed, then the overall mechanism of HLF reaction, along with the stepwise discussion of HLF reaction mechanism. That is, each step is discussed separately, also with the discussion of their movement to the product side, their stability, and etc. Hoffmann Loffler Freytag reaction was first time given by A.W. Hoffmann in 1878, about 1 century, more than 1 century, 150 years ago. And after that, in 1909, K. Loeffler and C. Freytag worked on the reaction mechanism of this Hoffmann reaction. Basically, this method is about the synthesis of pyrrolidines. This pyrrolidine uses the substrates of N-halogenated amines. These N-halogenated amines are converted into cyclic heterocyclic amine through an intramolecular 1,5 hydrogen atom transfer or hydrogen atom shifting to a nitrogen radical. So the conversion of this N-halogenated amines into pyrrolidines is achieved through the acidic conditions, followed by applying heat, thermal energy, or the sunlight in the form of visible light or UV light, and finally the product is achieved by the workup through the use of base. Here you go and see the general reaction in which an N-halogenated amine is converted into pyrrolidine. First step is the use of acid along with heat or sunlight, and second step is the use of base to finalize the product. In general form, it can be written is also that N-halogenated amine in which R1 can be alkyl, aryl, or hydrogen, and R2 can be alkyl, acyl, or hydrogen, and X can be chloro, bromo, or hydro, are treated in the presence of sunlight, heat or some radical initiator to get the delta halogenated amine. That is, this is an intermediate which is formed after 2 or 3 steps, and by the use of base we get the cyclic amine, which is also known as pyrrolidine. The conditions can be acidic or neutral or weakly basic medium, and we get the product of this pyrrolidine. These the conditions vary with the variation in the nature of the substrate. Here you can see the this reaction forms only 5-membered ring, and mostly or predominantly most of the time this 5-membered ring is achieved, is synthesized instead of some other ring. That is, the abstraction of proton is from the delta carbon, which is at the 4th position from the nitrogen, and we get the finally product. We shall discuss about the reason of this abstraction from this position on next slides. If we see the history of this Hoffmann HLF reaction, then in a first time in 1878, A.W. Hoffmann, who is the discoverer or inventor of this reaction, was basically working on the structure of the piperidine, which was unknown at that time, and he was considering that there is some unsaturation in piperidine, and he was to add hydrohalic acids or bromine into that double bond. But after a number of reactions, he obtained various N-haloamines or N-haloamides, and which were then studied under acidic and basic conditions for their different types of reactions. So the treatment of first reaction of Hoffmann was the treatment of 1-bromo-2-propyl piperidine with hot sulfuric acid, followed by some basic workup, and he yielded octahydroindolizine, a bicyclic tertiary amine. Here you can see the structure: N-bromo substrate, and then after acidic condition and temperature of 142 degrees C, that is thermal conditions, and then after the use of base as a workup, we get the cyclic ring of 5-membered cyclic ring. After then in 19 there was no work on this reaction furthermore, and about 29 or 30 years after, in 1909, K. Loffler and C. Freytag noted the transformation of some simple secondary amines into pyrrolidines, and they worked on the synthesis of nicotine from N-bromo N-methyl 4-pyridine 3-irbutane 1-amine. Here you can see the structure of this substrate, which was converted into nicotine molecule, and so through this synthesis they worked on the reaction of Hoffmann, and therefore after that this reaction was named Hoffmann Loffler and Freytag reaction. Here are some general features of this HLF reaction. First, the starting material for this reaction can be N-chloro, N-bromo or N-iodoamines. Most of the time N-chloro or N-iodo is used, but the most active one are the iodoamines. For thermal initiation, N-chloroamines gives better yield because N-bromoamines are thermally less stable. So therefore N-chloroamines give better yield in the thermal condition. But in the conditions of UV irradiation, the N-bromoamines give better yields of pyrrolidines as compared to N-chloroamines. The third feature is of this reaction is that this is carried out in acidic conditions, but thereafter some modifications it has been achieved that we can proceed through this reaction in neutral conditions or even weakly basic conditions, and the yields obtained are reasonably considerable. Next feature of this reaction is that it can be conducted under milder conditions provided that the alkyl radical is stabilized by an adjacent heteroatom, for example nitrogen. If the substrate molecule contains a heteroatom at the adjacent position of the alkyl radical, which is being produced in as an intermediate in the pathway of the reaction, then that heteroatom can stabilize the alkyl radical, and we get the reaction or we get the product even in mild conditions and not so vigorous conditions. Initiation of radical process can be through heating. It was discovered that this process moves through the radical formation, and this radical formation, initiation of the radical process can be achieved through heating of the N-chloro, N-bromo or N-iodo substrate, or through irradiation with UV light, visible light or UV light, or with some radical initiators. Radical initiators include dialkyl peroxides, as we know that two oxygens are attached with each other in peroxides, and metal salts. You are familiar with the peroxides and the nature of the production of radicals, how oxygen-oxygen bond is broken and we get the alkoxide radical which precedes the reaction. But what about the metal salts? Here is the example for this metal salt reaction, that an alkyl halide is treated with copper 1 chloro, some ligand is attached with it, and we get R radical plus cupric. First reactant was the cuprous chloride, now we get cupric chloride along with ligands attached to copper. The metal salts are also the source of the radicals for the initiation step. Initially the formed nitrogen center radicals abstracts proton from delta position 5-membered 5 position and predominantly 5-membered ring is obtained. 6-membered rings are also known up to some extent, but they are too much rare, and due to rigidity of some cyclic systems, we can get the 6-membered rings in some reasonable percentage, but most of the time predominantly we get the 5-membered ring, that is pyrrolidine, as the final product. The study of the mechanism for this HLF reaction was performed in about 1949 by Wazonik and Thilan. It is about you can see 70 years after the invention of this reaction. The full mechanism of the reaction was studied and clarified. In 1949, Wazonik and Thilan studied the cyclization of N-chloro N-methyl cyclooctylamine. The structure is shown in the form of reaction here. They reacted this in the presence of sulfuric acid with chlorine in UV irradiation, number 1, and number 2 in the presence of H2O2 hydrogen peroxide as a radical initiator in dark, and they get N-methyl granatine, which was 24% product yield, but this yield is much more as compared to that formed without light or peroxide. That is, the product formed in darkness was too much low, or the product formed in the presence of in the absence of hydrogen peroxide as a radical initiator, the yield was too low. This reaction clarified the reaction mechanism of this HLF reaction. They concluded that reaction proceed through a radical chain mechanism, and the steps are specifically, first step is the protonation of N-chloroamine by the acid, and then second step is the homolytic cleavage of this N-chlorine bond. NCl bond is homolytically cleaved by heat, thermal energy, or by light, or some other initiators like hydrogen peroxide or other organic peroxides, and we get the aminium ion as a radical and chloride as a free radical. In the next step, this aminium radical intramolecularly abstracts a sterically favored proton from the chain, and we get the alkyl radical. Alkyl radical is converted into alkyl halide by the abstraction of halogen from the protonated substrate, that is the protonated substrate which was formed in the first step when N-chloroamine was protonated by the acid. This protonated species is used to abstract chlorine halogen, and we get alkyl halide, and on the other end we also get a free radical. So in this way a chain starts. In the next step, this alkyl halide is cyclized in the presence of a base. Here like this here was used an alkali. In this reaction an alkali was used, and we get the product in the form of a tertiary amine. This base is necessary for the conversion of this alkyl halide into cyclic or heterocyclic amine. So this was the overall an overview of mechanism which was proposed by Wazonik and Thilan, and actually it is the final and recommended mechanism by the other scientists also. Here is the overall mechanism of this HLF reaction. The first step is the protonation of this chlorinated amine. Here is it can be any haloamine, but here is the case, in this case is chloroamine, which is protonated by an acid like sulfuric acid generally used in high concentration, and we get the ammonium ion. In the next step, this ammonium ion is homolytically cleaved into chlorine free radical and nitrogen free radical. This nitrogen free radical with positive charge is also named as aminium ion. This aminium ion can be represented in a cyclic manner. As you can see here, this is showing a 6-membered ring. Through this 6-membered ring, transition state of this 6-membered ring, this reaction, this species goes into 1,5 hydrogen atom abstraction, and we get the radical on carbon instead of nitrogen. Here you can see the way of mechanism, that one electron from nitrogen is moving toward the hydrogen, and the carbon hydrogen bond is broken in such a way that hydrogen comes with its electron towards nitrogen, and we get the formation of NH bond, and simultaneously the CH bond is broken, and we get the carbon with a free radical on it. This mechanism is also thought to be a move in a concerted manner. Here you can see this will surely move in concerted way. At the same time the bond will be formed, and the same time the old bond will be broken. In the next step, this carbon free radical is treated with the first protonated chlorinated amine, that we termed as ammonium, before the step of homolytic cleavage. So this chlorinated ammonium is now acting as a chlorinating agent, and it will provide chloride in the form of chlorine radical. This chlorine radical will attach with this carbon radical, and we get an alkyl halide. At the same time, we will get the free radical on nitrogen with positive, that is ammonium ion, ammonium radical. In this way, this sort of a propagation moves on, and we get radical chain from this reaction. We also term this step as propagation. The first step was the initiation, in which free radicals were produced through homolytic cleavage, and this step is the propagation of free radicals, in which chains is moving in the form of free radical. One free radical is finished, and at the same time another free radical is created. In the next step, this ammonium alkyl halide containing ammonium species is treated with the base. The base abstracts a proton from nitrogen, this ammonium ion, and we get the lone pair of nitrogen free. This lone pair, acting as a nucleophile, attacks on the carbon bearing the halo group in a SN2 reaction mechanism, and the chlorine is abstracted in as a chloride ion. Cl minus ion is separated, and we get the cyclized ring, in which nitrogen is with positive charge because of formation of 4 bonds. In the next step, again other molecule of base comes and abstracts another proton of nitrogen, and we get the neutral pyrrolidine structure. At the time of workup, this species is worked up in acidic medium because there should be basic medium, because if we apply the acidic medium, then this nitrogen will protonated again, and this positive cation will be solubilized by the medium, and we will not be able to get the product. So this product should be obtained in a slight acidic medium, slight basic medium instead of acidic medium. This is also the mechanism of this HLF reaction, but it is presented in some different way for better understanding of this reaction. Here you can see the generalized N-haloamine, which is protonated by the acid, and we get the ammonium cation. This ammonium cation is treated with heat, thermal, or with sunlight or UV light, or radical initiator. Mostly UV light, ultraviolet radiations are used for the homolytic cleavage, but sometimes if we have some substrates of some better activity or conditions, or acidic conditions, or medium is in such a way favoring the product, then sunlight can be enough for the process. And we get here, after the homolytic cleavage of this NX bond, we get the free radicals, in which one is halo radical is removed, another we get the ammonium radical. This ammonium radical moves through a concentrated radical, moves through the mechanism in which we get the formation of NH bond and the breakage of CH bond through 1,5 hydrogen abstraction, 1,5 hydrogen shift. I think we have discussed in some last steps lectures, one of the last lecture, that how this numbering 1,5 is nominated. I can repeat here. The bond which is going to be broken is termed as 1. Both atoms of that bond are termed as 1. Carbon is number 1. Here the delta carbon is number 1, and hydrogen is also numbered 1. If delta carbon is number 1, then gamma will be 2, beta will be 3, alpha will be 4, and nitrogen will be 5. So the proton is shifting from one carbon position to fifth position, and we get 1,5 hydrogen abstraction, hydrogen shifting. And in the end we get an alkyl radical. This alkyl radical here is mostly it can be I think it should not be said mostly it can be primary. If R1 group is not attached with this carbon, then this carbon radical will be primary radical, and here is the case, this carbon is secondary, but it can also be tertiary. And we know that about the stability of the radicals, that primary tertiary free radicals are more stable as compared to secondary and then as compared to primary. So the preference, if there are chances for the free radical, more than one types of carbons are available for the formation of free radical, then that free radical will be found preferably which is more stable, that is tertiary will be favored over secondary, or primary or secondary will be favored over primary. Here in this case there is no competition like this, and so we get the secondary free radical. This secondary free radical here is shown to be attached with the halo free radical which were produced in the homolytic cleavage step. This carbon free radical attaches with this halo free radical, and we get the alkyl halide. And in the last mechanism, if you remember, we get this halo free radical from the ammonium cation which was produced in the first step of protonation. If we compare the chances, then we come to know that the haloamine, that is reactant, is more in concentration as compared to that of free radical, because we have taken let's suppose we have taken 10 molecules of n-haloamines, then after protonation all of them will be converted into that protonation, but hemolytic cleavage will be take time, and there will be less number of molecules which are producing or which are in the form of n radical or x halo radical. So I think there will be more concentration of this ammonium cation produced in the first step by protonation, and there will be formation of this alkyl lead through this instead of this halo. So therefore this is a reaction mechanism is given here for the comparison with the last mechanism, so that you can understand better what are the more chances for this reaction. So this gamma halogenated amine is then treated with the base abstracts the proton and makes the nitrogen lone pair free, which acting as a nucleophile removes the carbon, removes the halo group from the carbon, and we get the nitrogen carbon bond formation in the form of a 5-membered cyclic ring. This halo formed is removed by the base, or you can see the positive cation of the base. In the next step, another proton is also abstracted by the base, and we get the finally cyclic amine. And this amine is obtained here in the basic media. That is, the workup includes the basic medium. The first step of this mechanism is the protonation of n-haloamines. Here the taken example is n-chloroamine, which is protonated by acid. Acid can be any acid like sulfuric acid, inorganic acids like sulfuric acid, or hydrochloric acid, but most of the time sulfuric acid is used in the list of inorganic acid. In the list of organic acids, trifluoroacetic acid is used generally. After the protonation, we get the ammonium cation. Here is the question: why the 3 lone pairs of chlorine are not attacking the proton? If you compare the lone pair, nitrogen bears 1 lone pair, but chlorine bears 3 lone pairs. 3 lone pairs mean, as you know, chlorine has 7 electrons in its valence shell. So one is bonded through covalent bond, and there will be 6 electrons available in the valence shell of chlorine, so there will be 3 lone pairs of chlorine. But the attack is not from these 3 lone pair of chlorine, but is attack from the nitrogen having 1 lone pair. Both are electronegative, both are non-metals. Nitrogen and chlorine, both elements are non-metal, both are electronegative, have ability to attract the electron to make negative anions. But the attack, the nucleophilic character of nitrogen is higher as compared to that of chlorine. The reason for this higher nucleophilicity of nitrogen can be explained through the size of the nitrogen, which is greater as compared to that of chlorine, which is smaller in size. So due to small size, the lone pairs are strongly attracted towards the nucleus, and so we are unable to make these lone pairs to attack on the proton. So the attack is from the lone pair of nitrogen having high nucleophilicity on the proton from the acid. The second step was the free radical formation. Here you can see the homolytic cleavage in which N chlorine bond is broken and we get the chlorine free radical and the aminium cation free radical. First thing, what do you mean by the homolytic cleavage? Is the cleavage in which the bond is broken in such a way that both the shared electrons are moved towards their respective atoms. That is, bond is broken in such a way that each atom making that bond moves away by its own electron. There will be no positive or negative charge due to this bond breakage or any of the species. If there is a charge on the atoms or one of the atom due to breakage of bond, then it will be it will not be homolytic cleavage, then it will be heterolytic cleavage. Heterolytic cleavage means bond is broken in such a way that 2 electrons are taken by one of the atom, and that atom which takes away the both electrons is shown with the negative charge, and the other atom whose electron is given to the other atom is shown with positive charge. Here in this case the nitrogen is already positively charged due to 4 number of bonds, so this positive charge is not due to this bond cleavage of nitrogen and chlorine, but the nitrogen gets the free radical unpaired electron on it due to this homolytic cleavage. If we compare the difference, for example, if you break the chlorine bond, you will get 2 chlorine free radical, but if you break the 2 oxygen double bond, then you will not get the oxygen free radical, you will get the atomic oxygen. So what is the difference between atomic oxygen and a free radical? A free radical is termed as that thing which has unpaired electron in its valence shell, but if a species has paired electron, then it will not be termed as a free radical, but it can be termed as a atomic oxygen, like that. Oxygen, you know, has 6 electrons in its valence shell. After breaking of double bond, you will get the oxygen from O2 molecule with 6 electrons in its valence shell. There will be no unpaired electron, so it cannot be termed as an oxygen free radical. It will be termed as atomic oxygen. Second point is that we are applying simply thermal energy or heat energy, or you can see light energy, UV light or sunlight, and this energy is breaking this nitrogen chlorine bond and not the other bonds like nitrogen hydrogen bond, nitrogen carbon bond, carbon carbon bond, carbon hydrogen bond. There are different 5 types of bonds, but we are getting only the cleavage of this nitrogen chlorine bond. So the you can see the mechanism of this homolytic cleavage, that the thermal energy or heat energy or sunlight energy provided in the form of sunlight or UV light will break that bond, that is a weak bond. Only that bond will be broken, which is the weakest of all the bonds. Here is given the question why only NCl bond is cleaved, and the answer is also written in the form of bond energy of different bonds. You can see the nitrogen chlorine bond energy is the least one among all of these bonds, and so the due to less bond energy or weak bond, this nitrogen chlorine bond is easily broken as compared to other bonds. Here we can explain why this bond is a weaker bond, but I think it will be too high here. You may explain yourself here. To avoid too much time on it, I move to other next steps. Third step is the 1,5 hydrogen shift. In the next step, this ammonium cation free radical move towards the cyclic. Here you can see the 6-member transition state is happening, in which nitrogen hydrogen bond is forming due to cleavage of carbon hydrogen bond, and the carbon free radical is producing. Two things are factorizing, or you can say governing this step. One step is the stability of the produced free radical, that is, here is the only one chance there is secondary free radical which will be produced, and second is the stability of the transition state. Here you can see the stability of this 6-member transition state, in which large groups are more kept on the chair form of cyclohexane, and this due to stability of this 6-member transition state, we get this transition state to move during the process of reaction, and so the product we get is 5-membered ring always, and there are less chances, or there are certain if there is steric hindrance available in this thing, then there will be 6-membered ring formation. Otherwise, most of the time 5-membered ring formation occurs. Here is the step 4, which is alkyl halide formation. The previously prepared carbon free radical is now involved in the formation of alkyl halide. It is attacking the ammonium cation, which was produced in the first step after the protonation of N-chloroamine. The chlorine free radical is produced, which move towards the carbon in a concerted manner, and we get the carbon chlorine bond formation, that is alkyl halide bond is formed, and at the same time we get the ammonium free radical. So this ammonium free radical can move into the product further. This thing was also achieved through the direct interaction with the chlorine free radical only to form the alkyl halide, and we have also discussed in the last slides about the relative formation of this, that the first step, that is the getting the chlorine free radical from the ammonium and nitrogen chlorine N-chloroammonium species, which was produced in the first step of protonation. It has the more chances for the formation of alkyl halide. The last step, which is the 5th step, is about the pyrrolidine formation through base. Here you can see the ammonium alkyl halide containing ammonium species also. Here nitrogen has 4 bonds, 2 with carbon and 2 with 2 hydrogen. Both of these 2 protons have been abstracted through base in 2 steps. In the first step, when one proton is abstracted, nitrogen gets its lone pair free. This lone pair, acting as a nucleophile, attacks on the carbon, and we get the breakage of carbon chlorine bond in SN2 reaction mechanism, and the chloride ion is balanced by the cation of this base. In the next step, the other proton is also abstracted by the proton by the base with the formation of water, and we get the nitrogen free from positive charge, and we get neutral pyrrolidine structure. So in this way, pyrrolidine derivatives are formed by the using an acid sunlight or thermal energy, and finally at the last step the use of base. This final product is obtained in from a basic medium. So this was overall about today's lecture about the introduction and reaction mechanism, and so next we shall discuss about the different modifications and some characteristics of this reaction involving stereochemistry, etc., and also the synthetic applications of this reaction.